So in this video, we are going to talk about ionic bonds, how to determine the charge of specific ions using the periodic table, how to draw ionic compounds, and examine a few of the properties that we talked about in our ionic bonding or ionic compound lab. Before we start talking about ionic bonds, just general information about chemical bonds. Any sort of chemical bond is an attraction force that holds atoms together. We're going to talk about that attraction force specifically for each of the three types of bonds that we discuss. So we'll talk about what the attraction force is for ionic bonds a little bit later in this video, but it does boil down to the behavior of electrons and how those act with the atoms. So electrons can either be shared between atoms or they can be transferred. And when we're talking about ionic things, the electrons are being transferred in those compounds. So they're actually moving from one atom to another atom. This goes into the definition of ionic compounds. This definition is twofold, and you need to know both different parts. The first is that it has to have a metal or a non-metal. Of course, there's an exception to every rule, but 99% of the time, ionic bonds or ionic compounds have a metal and a non-metal in them. The second part is what's underlined here, is that the electrons, like I said before, are actually being transferred. So the full definition, ionic bonds are formed when metals transfer their electrons to non-metals. In this, they form ions. Ions are anything with a charge. We've talked about ions a lot lately, but I did want to review cations and anions because it seems to be a lot of people are confusing the two. So cations are anything that are positively charged. So those would be your metals on the left side of the periodic table. Some examples would be your sodium and aluminum metals that are shown there. Anions are negatively charged, so those are most often your nonmetals on the right hand side of the periodic table. One of my students came up with a way, or another way to remember this. If you look at anion, how it's spelled, he said that it stands for A negative ion. So if that helps you remember how or which one is negative and which one is positive, by all means go for it, use it, so you can remember that for your tests and quizzes. When we move to the actual attraction force for these compounds and what holds these atoms together, again, this one is twofold. So the transfer of electrons, the actual movement of that electron, forms your positive and negatively charged ion. So it forms the cation that is positive and your anion that is negative. You guys have all heard the saying opposites attract. So those oppositely charged ions then attract to each other, just like the opposite poles of a magnet are attracted to each other. So again, twofold. So transfer of electron and then the opposite things actually attracting to each other. We talked very briefly in our last lecture about the charge of electrons and where those come from. The whole point of bonding is so that atoms can become stable. However, atoms are lazy and they want to take the easiest way to get to stability. So if you look at all of the metals on the periodic table in general, they have a low number of valence electrons. I'll show you a periodic table in a second. With that low number, they can either gain a whole bunch of electrons to be stable, to get to that stable number of 8 electrons, or they can lose a smaller number of valence electrons. Metals typically choose to lose the small number of valence electrons to become positive or cations. The opposite is true for the nonmetals. So because they have a higher number of valence electrons, it's easier for them to gain electrons to become stable rather than lose. So when they gain electrons, they become negative anions. So if you look over here, you have your periodic table. Across the top, I've numbered the groups 1 through 8. Those I'm hoping remember from our periodic table unit. correspond to your number of valence electrons in each of the groups. So everything in hydrogen's family or group has 1 valence electrons. If you go to the other side of the periodic table, fluorine's family, all of the elements in that group or group 7 have 7 valence electrons. Transition metals in the middle, that big group, have a varying number, so we typically don't look at those right now. I will show you an example of how to draw an ionic compound with one of those a little bit later. But you can use your valence electrons to actually determine your charges. If you take a look at this, like I said, everything in hydrogen's family has 1 valence electron, so it can either gain 7 valence electrons to get to the stable number of 8, or it could just lose its 1. The easiest way out is to lose 1 valence electron. When doing that, it's losing a negative particle, so it's actually forming a positive 1 charge. It's opposite of what you would typically think, but it's all the way across the board the same way. So if you look at 2 valence electrons in group 2, it could either gain 6 to get to the stable number of 8 or lose 2. So it's going to take the path of least resistance and lose 2 valence electrons to become a positive 2 charge. If you skip over your transition metals and go to group 13, which has 3 valence electrons, it's going to lose 3 valence electrons instead of gaining 5. And when it does that, it becomes a positive 3 charge. If you skip towards the end, 7 valence electrons, group 17, that's fluorine's family, has 7 valence electrons. It can either gain 1 or lose all 7 of its valence electrons. It would rather gain 1 valence electron, so you're gaining a negative charge, and it actually becomes a negative 1 charge. Oxygen's family, or group 16, has 6 valence electrons. It can gain 2 valence electrons, or it could lose 6. The easier way is to gain 2 valence electrons and become a positive 2 charge. The last easy family is nitrogen's family, so that's group 15, has 5 valence electrons. It is going to gain 3 electrons to become a negative 3 charge. Now carbon's family, it doesn't take any more or less effort to gain 4 valence electrons or lose 4 valence electrons. So this family can either be positive or negative 4. It does have a general trend, however. If you look at the top of the group, these are consisting of mainly nonmetals. So these nonmetals are more likely to actually form a negative 4 charge to be like the other negative nonmetals. If you look at the bottom of the group, tin and lead are down there. Those are metals. Those are going to form a positive 4 charge to be more like the other metals on the periodic table and form cations. The last family, group 8 or 18, all the way on the end, that family already has a stable number of valence electrons, so they are not going to form a charge. So we say those are electrically neutral or have a charge of 0. Next, we're going to look at a few examples on how to show ionic bonds in compounds. If you look at this example, I have aluminum combining with oxygen. If you take a look at where those are located on the periodic table, aluminum is right here, so you have 3 valence electrons. Oxygen is over here, has 6 valence electrons. So you can see the red dots indicate their number of valence electrons. Aluminum has a smaller number of valence electrons, so that one actually wants to become positive. It's a metal. That's another way you know that it's going to be a positive cation. You can see in this picture that both aluminum ions are actually losing 3 valence electrons, so they both have to do the same thing. You can't have one losing 3 electrons and another one only losing 2. They have to do the same thing. They have to be identical. So they both become a positive 3 charge. The 6 valence electrons between the two of them are dispersed between 3 different oxygen atoms. Each of the oxygens gain 2 of the valence electrons, forming negative 2 charges. Again, all of them are doing the same thing. You need to make sure that you show The arrows include the arrowheads. Don't just draw lines, because you need to show your transfer of electrons, show where it's coming from, where it's going to, so you can show your ions actually being formed. If you take a look at this, you can also use this image to determine the formula between oxygen and aluminum that is formed. Make sure that you know your aluminums or the cations are always listed first. So you read left to right. Positives are on the left side of the periodic table. That's where all of your metals are. Negatives are on the right hand side. So you're going to start with your positives. So you're going to start with aluminum in this case. We had to draw 2 aluminums to make everything stable, so that's why we get the Al2. And then we have oxygen next, and we needed 3 oxygens in order to make everything stable. So your formula would be Al2O3. Notice how I don't include any formulas, or sorry, I don't include any charges in my final formula. Moving on to the next example. This one has gold 4 and sulfur in it. First off, I just want you guys to know that you do need to make sure you know your Roman numerals. I have them listed over here, 1 through 7. Those are the only ones I'm going to make you know. But you do need to make sure you know what those mean, because those are key when you have a transition metal. So if you take a look at your periodic table, you guys can see that gold is indeed a transition metal. It's over here in the section where we don't have a pattern to determine our valence electrons in gold, so that's why you need your Roman numerals. The other one, sulfur, is going to look just like your oxygen. It has 6 valence electrons because it's in the same family. So the valence electrons for your gold are depicted from those those Roman numerals. So those tell you your number, if I can get my pen to work, of valence electrons. So make sure you know that. Make sure you make a note of that in or on your note sheet. So with that, gold Au has 4 valence electrons, or 4 dots around it. Sulfur has 6 valence electrons. Gold has less, so it's actually going to become the positive ion. It's going to lose its electrons. Where sulfur has more valence electrons, it's going to be negative. It would rather gain 2 more electrons than to have to lose all 6. So we are going to draw our arrows so you can see the bonds being formed or the electrons transferring. Again, make sure you use actual arrows, not just lines, so you can show the transfer. When you do that, you can see that between the 3 atoms there, everything becomes stable. You can add up your charges, the +4, the -2, and the other -2. You get a charge of 0, which is electrically neutral, so you know everything is stable. So then you can go ahead and write your formula. Your formula, again, always starts with your positive ion, so Au is first, and then sulfur is second. We only have 1 Au, but we have 2 sulfurs, so you get AuS2 for your final formula for that example. Moving on to the last section of a couple of properties of ionic compounds. The first thing you need to know is ionic compounds do not form what we call molecules. That is a vocab term that we only use with covalent compounds. Ionic compounds form things called networks, and I have an example of a network down here at the bottom. You can see the alternating positive and negative charges. The red and the blue are alternating. Know that when I give you a formula, if we go back to our example over here of AuS2, that doesn't tell you that you're only using one gold and 2 sulfurs to form a crystal of gold sulfide. That's just showing you your ratio of, for every 1 gold atom, you have to have 2 sulfurs to balance it out. In the case of salt or sodium chloride, you have 1 sodium atom for every 1 chlorine atom to balance those out, because one's positive 1, one's negative 1. So ionic compounds form networks. You need to know that they're alternating positive, negative charges, and they show ratios of the numbers, and that's how this crystal structure actually forms. So in this case, the salt that is actually forming, you guys saw the little cubes that are formed from salt with the microscopes in lab. If you move to our second ionic compound property, we're going to talk about conductivity. This first picture over here just talks about, or it shows you the conductivity of distilled water, so you guys can see that the light bulb does not turn on, meaning that there's nothing in the water to actually carry an electrical current. So if I had just had distilled water, you wouldn't have to worry about swimming in the water because it can't carry an electrical current. So the whole lightning thing wouldn't matter. If you go to the second picture here, you guys can see the conductivity tester in solid salt. You guys can also see the zoomed in picture of the ionic network of alternating positives and negative charges. This one also does not carry an electrical current. The light bulb does not turn on because in this case, the ions are actually stuck in that network. They have to be alternating, otherwise they wouldn't be attracting to each other, and they can't move out of that network. So because of that, there's nothing to carry the current between the different electrodes of the conductivity tester. So no current is formed. The last one over here, you have salt actually dissolved in the water, and in that one, the ions break apart and are able to flow with the water molecules. Because the ions can actually move, you have charged particles that are moving. Those are the two things that need to occur for something to be able to carry an electrical current. And in this case, you guys can see that the light bulb is actually turned on. The last thing I want to talk about is writing ionic formulas. We touched on this briefly with our examples, but this is a way to do it without actually having to draw out the entire compound. So you guys can see here at the bottom, first example is aluminum fluoride. Al is a +3 ion, fluorine is a -1 ion. You can write these multiple times. So right now you see that you have a +3 and a -1. If I write another fluorine, I can see that I now have a +3 -2. So I'm going to need one more fluorine to balance out my +3 charge. So I end up with Al 1, and the 1 is assumed, just like before. AlF3 would be the formula for that one. Titanium nitride. Titanium is Ti on the periodic table. This Roman numeral 3 tells you that it is a +3 charge. Nitrogen on the periodic table is a -3 charge. And so you can see that you're already balanced +3 -3. So with this, you can just go ahead and erase your charges, and your final formula is TiN with no numbers because it's a 1-to-1 ratio. Notice how in both formulas, you do not include any charges in the final formula. I hope this video helped you review ionic compounds, remember how to form charges for specific ions, how to draw ionic compounds, and touched on a little